Let's look now at the second half of exponents, and this is where we're going to apply exponential functions to solve problems involving things like growth, decay, and compound interest. Now, as we work our way through these problems, we're going to look at a variety of real-world situations. They may seem unique to each question, but it's really just a variation of the exponential function. Y equals b to the x, where we're either trying to find the base, the exponent, or the value of y. But they're all just exponential functions applied to certain situations. Here's the first one, compound interest. And compound interest deals with money, where money is added to your previous money and it keeps building up. Compound interest. This is calculated on the principal, and then it is added to the investment, so it builds up over time. And compound interest is calculated this way. A is the final amount that we end up with after the compounding has occurred. P is what we call the principal. That's the amount that we start with. R is the annual interest rate, and we often get it as a fraction or we get it as a percentage. We want to convert that to a decimal. N is the number of compounding periods in a year. So sometimes that is monthly, which is 12, or semi-annually, which is twice a year. And T is the number of years that we are investing our money away. And this is just a simple compound interest equation where we are given these values and we have to find something about it. So let's apply it in a situation like this. The interest earned if $2,500 is invested at 8.5%, and what this little notation means is per annum, which is Latin for really just per year. So you may see per year or might see this per annum. 8.5% per year compounded semi-annually for 4 years. So what we want to do with this word problem is take the information we know. Well, first we have an amount of money that we start with, our principal of $2,500. We know that the rate per year is 8.5%, which as a decimal is 0.085, and it's very important that we bring that 5 for our calculation. Our time in this case is 4 years, and what we have to consider is N, the number of compounding periods per year, and that's where this semi-annually comes into play. Semi-annually really means twice a year. And you might be familiar with this if you're paid semi-monthly, twice a month. Semi-annually is twice a year. So the number of times that we compound this is 2. Now the other way we can think about that is it's compounded every 6 months, but we're going to consider it twice a year. And now that we have all of our information, we're asked to find the amount at the end of the compounding period. So we just use our formula from above. P is equal to 1 plus R over N to the NT, and we just plug in our values. 2,500, 1 plus 0.085, and this is an important piece here. Why we have to take our R and divide it by 2 is we get 8.5% per year, not per compounding. So really what we're doing here is we're taking the 8.5% and we are cutting it in half. Each compound period gets cut in half because we have 2 periods per year. That's all that's doing in that calculation. N here is 2 times 4, which would mean we have 2,500, 1 plus 0.0425 all to the 8. And we could go one step further, 2,500 to the 1.0425, and this is where we can probably notice this is just an exponential. A base of 1.0425, an exponent of 8 multiplied by 2500. And at this point, just fire it in your calculator, and we get an end result equal to $3,487. And let's not forget the pennies here, 76 cents. There's our final amount. Now, the only thing we have to be careful about here is we want to find the interest earned. The interest earned. So if we start with $2,500 and in the end we have $34,87.76, the interest is going to be the difference. How much money was earned? So we just take our amount of $34,87.76 and we minus what we started with, our principal, and we'll find out that for 4 years of investing, we've earned $987.76. So pretty good if we can get an 8.5% interest rate compounded semi-annually for 4 years. The important thing to note, though, is it's just an exponential equation once we break it all down. Let's try another common type. And this deals with earthquakes or pH. The Richter or pH scale are really just power scales of 10. Meaning, in the function y equals b to the x, the base is 10 and the scale reading is x. So the important point here is to notice that the x value, the exponent, is the scale reading. Either the value on the Richter scale or the value on the pH scale. So let's apply this to our situation. We have 2 earthquakes, and we want to find out how many times more powerful is earthquake 1, measuring 8.4 on the Richter scale, compared to earthquake 2, measuring 4.2 on that same Richter scale. So earthquake 1, we want to find its intensity, or how powerful it is. The Richter scale, or its intensity, is just a base 10. And the exponent is the reading on the scale. So the first earthquake is 10 to the 8.4 intensity, which is a really, really big number. Earthquake 2 is 10 to the 4.2 on the Richter scale, which is still a really big number, but not as big as earthquake 1. We want to find out how much larger, or by what factor, does one compare to the other. How many times more powerful? And if that's the case, we know that earthquake 1 must be greater than earthquake 2. It's a larger value. And if we wanted to write this as an equation, that means earthquake 1 is equal to some constant value multiplied by earthquake 2. So it might be 1.5 times, or 2 times, or 3 times. What we really want to find is the value of K. How big is that K value? And all we do is take our 2 earthquake measures and divide them. Divide their intensities. Well, earthquake 1 was 10 to the 8.4, and earthquake 2 is 10 to the 4.2, and now we can use our rules for exponents. The base is the same, so we would subtract the exponents, 8.4 minus 4.2, and our intensity would be by some factor greater, just do that subtraction, of 10 to the 4.2. Now, if we actually want the intensity, then we have to find that value. What is 10 to the 4.2 on your calculator? And we just fire this in, and we'll get 15,800 and 49 if we round to the nearest there. So almost 16,000 times as great on the Richter scale. Now you can see why we use the Richter scale to give us a value that is more reasonable. If we're comparing 4.2 to 8.4, we can see that 8.4 is much bigger, but it's bigger based on base 10. It's almost 16,000 times as great. And we don't want to be in that kind of earthquake. So let's try one more here. And this deals with growth and decay. And we're going to talk about discrete growth and decay. And what this discrete growth and decay means that a certain types of growth or decay occurs at a specific rate over some period of time. So if we're told a growth, an example here is 7.5 growth, the R value, our rate, is just 7.5. If we have a depreciation, and depreciation means it is decreasing, a decrease of 15%. To find the R value, we must consider that we start at 100% and we minus 15% because we're depreciating. We would really have a rate of 85%, but we want to make sure we put that as a decimal of 0.85. So percentage, you got to be careful. Is it an increase or a decrease? Appreciation or depreciation? Well, if our population doubles, well, then that just tells us that our R value must be 2. If our population triples, it must be 3. And one you've seen in some science class, the decay, the half-life decay, our R value is a half. And all of those R values are really just the base in an exponential equation. And we're going to use this formula. F is going to represent the final amount. I is the initial amount, how much we start with. R is the rate of growth or decay, like we did above. T is the total time that has gone past, and P is the period of growth or decay as given to us in the question. So we're going to use this formula, but remember, it is again just a form of y equals b to the x, where we have other numbers in there and other variables, but it's just an exponential. So let's apply this. Here we have a photocopier, and it's set to reduce an image by 8%. We want to find what is the copy size after 4 reductions. Well, the first thing we want to notice here is our rate. It's a decrease of the image by 8%. You could probably do this in your head, but let's just show the calculation. 100% minus 8% is the same as 92%, which is really just 0.92 as a decimal. That's our R value. Now, the thing about this question is we actually don't have a final amount or an initial amount. We do have an R. We've just determined that R. And if we want to use our equation, our T over P is what we need to figure out. Well, T is the time that has actually occurred. And the time in this case would be 4 reductions. That's given to us in the question. And the P, the period for one reduction, and this is what's unique about questions like this, is each time we do a reduction, we would just consider that one period. So if 4 reductions have occurred, the period is 1. And if you think about the photocopier, every time you push the button would be considered a period. So we've pushed this button 4 times, and the period is 1. So let's put that information in. F is going to equal I to the 0.92 to the 4 over 1. Well, we can go one step further, and we can say it's I to the 0.92 to the 4. And what we want to find out is the final amount, but we're going to refer to this based on the original. So we don't have an I. I is unknown. But we want to figure out what is the copy size in relation to the original I. Well, doing that, if the original was I, well, we can find out what this number is, and we just take 0.92 and fire it in your calculator, and we'll get 0.71639. And from here, we can actually answer our question. We don't know what the original I was, but we know that the final amount will be the original I multiplied by this decimal. Or we could say this another way, that the final amount will be 71.6% the size of the original. So we've reduced it down to 71.6% of the original. And sometimes that's all we need to know. What is the percentage that has been reduced or increased? And we're going to do more examples like this in class, and these formulas will become a little bit clearer as we work our way through the rest of the questions.